Matthias Diener, who is a postdoc at PPL. He's going to talk about using OpenMP offloading in Join++.
All right, good afternoon. So the last 2 days we've been talking a lot about accelerators. So even though maybe the top machine in the top 500 is not using accelerators, a lot of machines nowadays, they feature nodes that are heterogeneous. So where we have a host device, but we can also use accelerators such as GPUs. And in this context, one of the most important questions that we face is how do we efficiently program these accelerator devices? And what I'm going to talk about today briefly is to present one option, OpenMP, and discuss how that interacts with Charm++. So traditionally, we use specialized languages such as CUDA and OpenCL for developing code for accelerators. But these come with quite serious disadvantages. So in the case of CUDA, we can only target one specific type of device, so Nvidia GPUs. But even in the case of OpenCL, which supports more types of devices, we would often need to rewrite our application, or at least the kernels of the application, in a different programming language. So in this context, OpenMP can be an interesting option to program accelerated devices because recent versions of the standard, starting from 4.0, they have support in the standard and in the language for targeting accelerators, so for offloading code and data to accelerated devices. It's not only useful for GPUs, but you can also target, for example, Xeon Phis. One of the biggest advantages is that we don't need to duplicate code, so we can use the same code for running on the CPU, but also on the GPU. We furthermore can use standard languages, so we don't need to use a specialized language, and we can target, like I said, different types of accelerators. So to give you a very brief overview how that looks like, so I'm using here an example, Zaxby operation. So Zaxby is a vector operation with 3 vectors, x, y, and z, and we calculate z equals a times x plus y. So if we use normal OpenMP on the host, it's a very simple operation, right? We have perhaps a parallel loop where we perform this operation on the CPU. So if we want to run this code on the GPU, we have a very simple way to do that in OpenMP. We just need to add one pragma, the pragma OpenMP target, basically to enable execution on the GPU or any other kind of accelerated device. What this pragma does is basically it instructs the compiler to generate code for your offloading device. So that particular part of the code is going to be compiled basically twice, once for the host and once for the accelerator. And then at the runtime, this pragma instructs the OpenMP runtime to execute the code and to transfer the data that is used inside that section on an accelerator device, if it's possible. So if we have a device available and if that device can be targeted by the OpenMP runtime. And we also, like I said, we need to then usually copy the data used in that part of the section from and to the device. So this is a very basic, very simple example here, but it shows already that by adding just basically one line of code, you can target an accelerator. Now, there are many more additional options that we can do. For example, we can specify other data movement strategies. For example, we could keep data on the device and use that in multiple kernels. So imagining that we have another kernel running after that. We can also select multiple devices. So there are ways, if one node contains, let's say, 2 GPUs or 4 GPUs, we can access these GPUs separately and run potentially a part of the problem on each GPU. So like I said, this is very simple. So the code essentially is unmodified except for the additional pragma. Here in this example, we have implicit data movement. So the programmer does not have to worry about which data needs to be moved to the device. But like I said, we can also do this explicitly. And in this example here, all of the calculation is done then on the device if one is available. Talk a little bit about the compiler support. So one of the main challenges for this OpenMP offloading is that the compiler support currently is not available in all compilers for all types of devices. This is the table kind of collected over the time. We can see that for most compilers, at least, we have at least some support for some OpenMP constructs and for some device types. But there are also there's a big difference between the amount of support available currently. Now, some other limitations are that we often can only do static linking, so we cannot put code that's potentially offloaded in a shared library. We often need a recent linker version, so for many compilers, this is based on link time optimization, so we need very recent versions of the bin utils, for example. Often C++ exceptions are not available, so we need to compile the code without support for exceptions. And also not all operations are always offloadable. This is depending on what kind of support the OpenMP runtime supports for which type of device. Now, often I/O, for example, is an issue. One other very important aspect is, of course, what's the performance like? Here we'll present performance on two different systems. Here the first system is an Nvidia Kepler K40. I compare here basically the OpenMP CPU execution on the host only in blue, then the OpenMP GPU on the device in orange, and in gray a comparison code that was manually implemented in CUDA. So the operation is the ZXP that I mentioned before. And this is running with GCC 7.3, so it's the currently most recent version of GCC. So what we can see here is that basically, depending on the number of vector elements that we have in our three vectors, we see that it makes only sense to run on the GPU for different sizes of input vectors that are larger than a certain threshold. Now we can also see that for smaller input sizes, for example, here for 1 million elements, there's still a very sizable difference between CUDA and OpenMP, about a factor of more or less 10x. The reason here is that OpenMP, the offloading has a very high startup overhead on GCC. You can see here that the total execution time for the kernel is almost flat. But we can also see as soon as we increase the input sizes, the execution times between CUDA and OpenMP are becoming closer to each other. In the best case for GCC, we have, I think it's about a 2x difference of performance. So this is for GCC. For another compiler for XL, the situation looks kind of similar, but it's a bit better for OpenMP. So we can see a similar difference in performance for very small input sizes. We can also see that the actual execution time gets closer and closer as soon as we have more vector elements. So in this case here, there's about 3-4% difference between CUDA and OpenMP on the GPU. So in the second part, I would like to briefly discuss how we can use this OpenMP offloading in Jump++ and AMPI. So as you probably heard yesterday in the presentation from Samyang, Jump++ has some support for an integrated OpenMP. That's based on LLVM, but that comes currently without offloading, so we cannot use this integrated OpenMP for offloading to the GPU. So what we have to do now in order to use this on the current version of Jump++, we can build Jump++ as usual, but we have to use a compiler to build Jump++ that can do some kind of offloading. So it needs to be a GCC that has offloading enabled, or XL, or any of these compilers. We cannot specify then the OpenMP option, which would use the integrated OpenMP runtime of Jump++. But there's also no need to specify something like fopenmp or enable OpenMP support when building Jump++.
No need or should not?
There's no need. It doesn't make a difference.
It's okay to specify?
It's okay to specify, yes. Now, because Jump++ itself doesn't use OpenMP inside. As soon as we have this version of Jump++, we can then build our application using OpenMP as we would in a normal application. We can use the OpenMP parameters and the runtime functions as normal. The only thing that we need to take care of is if we have something like load balancing or fault tolerance. So any system that does some migration, we need to take care that the data consistency is guaranteed between the host and the GPU. So what we need to do is update basically the data on the host from the data of the GPU. But as soon as we have modified the application in this way, then we can compile the Jump++ application normally with JumpC or AMP ICC, but specifying then, of course, the compiler's OpenMP and offloading options. So in the case of GCC, it would be FOpenMP. In the case of XL would be this QSMP, QOffload. I implemented this for an example application, a very small Jacobi stencil. I modified this to use OpenMP internally. The results I'm going to show here are based on the Ray machine, which is a Power 8 machine with a P100 GPU. The results here are also based on the IBM XL compiler. I'm comparing here two input sets, a small input set with 1 million points and a larger one that has 10 times the number of points. As you can see, there's, as we expect, a significant performance difference between running on the CPU and running on the GPU. For the small input set, it's about a 3x difference. For the larger input, it's almost 5x. Another interesting feature is that with the offloaded OpenMP, you can also use most of the tools that Nvidia provides, such as the Visual Profiler or the GDB version of that's supporting CUDA. So this is again for the Jacobi that I presented before. So just to briefly summarize, so OpenMP provides, I think, in a very interesting way to use accelerators. It's very simple to add support. Performance results are not great yet on GPUs compared to CUDA, but I think in the coming months we will see a lot of improvement in that regard. The main challenge currently, apart from performance, also that we need a more comprehensive support in the compilers. And the current version can be used relatively easily for Jump++ and AMPI applications. The two next steps that are interesting here for us is we want to evaluate if we can extend the integrated OpenMP with offloading support. So that would mean adding another library from LLVM to Jump++. And also we would like to see how we can interface with the GPU manager, about which I think you will have also a presentation. Okay, thank you.
Have you had a chance to get any comparison data on like KNL or other accelerators?
I've tried to do this on the KNC. The KNL, I don't know if the accelerator KNL exists. I don't have access to any machine that has an accelerator KNL. I've tried on the KNC and the performance was very good, so better than on the GPU. So it's at least for GCC, the first target architecture was really the KNC. That's why it was integrated basically. So it's a bit more mature, the support. For the Nvidia GPU, the support was only integrated for GCC version 7. So version 7, which is the current version, was the first version that has Nvidia GPU support.
Thank you.